Okay, for Algebra 1, we are doing chapter or section, pardon me, 5.4, using graphs. All right, so our objectives today are one, we're going to draw and interpret graphs, more on the interpreting side. Actually, we're going to draw in some graphs that represent real world relationships. Whew. You're going to do more of the drawing in class. Or in homework, pardon me. So you will often need to draw or interpret graphs that model real life situations. And this is called mathematical modeling, okay, when this is done. We've talked about this a little bit, but on your horizontal axis, you're going to have the x, and that's your independent variable. We've talked about this yesterday and even last week a little bit. Your vertical axis is your y, and is your dependent variable. So on the graph, those two things are already laid out for you. They're already presented. It's the same thing in science. If you would talk to Mr. Ryder or Mr. Daniels, this is what's happening. Okay. All right, so let's look at this. We've got this graph. Okay, it says growth of a largemouth bass. We have the age in years down here at the bottom. So that's our independent variable, because it's on the x. And we have the length, which is our dependent variable, because it's on our y-axis. So the length depends on the age. All right, so it says, here we are, draw a smooth curve to connect the points so approximations and predictions can be made. Okay, so we have the set of points, but we want to make an approximation or a prediction about some other things. So we're going to start here and we're going to smoothly connect those. It's a little harder. There we go. Pardon the screeching sound. So we've got this smooth connection. All right, because we're going to use that to predict the length of a 1.5-year-old bass. All right, so let's think about that. So we have a bass, and we want to go, it's 1.5, so in between 1 and 2. So we want to come up in between 1 and 2 here, okay? And then we need to follow that over and see what that measurement is. So between 1.5, and if I follow that over, I got, did I do 1.5 correctly? Oh, I got a little crooked. See, I was like, that doesn't look quite right. Let me go back. Because I'm standing up here and leaned over at an angle. It's actually a lot harder that way than going straight up. So if I went straight up to, there we go, that's a straighter line, and then went over, how long would that bass be? What would its length be? All right, great. It's about 9 inches. Okay, the next question is slightly different, okay, because it's saying about how old is a 15-inch bass. This time we're looking at the inches. So we're going to go up to 15 inches right here. How old is it? So we need to make that line go across to here. And then we need to bring that down, right? So where does that intersect down here? Well, it's right in between 3 and 4. So it's about 3.5 years old. Okay, so a 15-inch bass is about 3.5 years old. Again, your lines are hopefully a little straighter than mine. But, so we're using, again, we can connect these points. We draw smooth curves or we draw straight lines, whatever the points are. A lot of times they're going to be curves to connect them so we can make approximations and predictions. All right, so let's look at the next one, which is actual example 1. Okay, so this one says model, so the model's been done for you. I went ahead and did all that, or just copied it out of the book so we could save some time. It says model the first class postage rate data given in the table and state the general characteristics of the rate of increase of postage over the years. Predict what the postage rate will be in 2015, or 2050, pardon me. Okay, so we've got our year is our x-axis, so our independent, and our dependent is the stamp cost there. Okay, and so we've got all three of these tables combined into this graph. All right, so the first thing we want to do is draw that line, okay? So we kind of start here, right? There wasn't any, 1865 was our first stamp, so we start here, kind of goes down, we're going to follow that and come up. Okay, so it kind of keeps going up. All right, so it says, state the general characteristics of the rate of increase over the years. So what could you tell me? This part of the graph I think is really interesting, right? From here to here, what happened to the postage, the cost? Yeah, it went down. Okay, so the rate decreased slightly. So we could say the rate decreased slightly, pardon me. We could say the rate decreased slightly early on, or we could even give the year. We could say because we can see here, right, it was 6 and then 2 and then 3 and then 3. Okay, so we could say the rate decreased slightly in the beginning. Okay, let me put so it's a complete sentence here. All right, so how about the next section of the graph? So like, what do you notice is happening from here to like here? What about the rate? It stayed pretty steady, right? And that's like from 1875 to like 1975. So then we could say the rate stayed steady for about 100 years. And then how about that last part of the graph? So starting here all the way up to our last point in there. What can we say about that part of the graph? The rates have increased. I mean, that's pretty big increase too in comparison. So how would you describe that? Like, would you say a big increase or a significant increase, a rapid increase, dramatic? All right, so we could say the rates have, let's go with dramatically. Dramatically increased in recent years. Okay, that takes care of the whole graph there. We didn't write it out, but we should. What's our independent variable again? Okay, good. Our independent variable is the year. And the price, right, or the cost, is our dependent. So our dependent variable equals the cost. Okay, so we should go ahead and put that in the general characteristics. How about this last question? It says predict the postage rate, what the postage rate will be in 2050. What will the postage rate be in 2050? Well, if we, again, go down here to 2050 and we trace that up, it's about there, and bring that over. Okay, so in 2050, it'll be approximately 80 cents if it continues to go at the rate at which it's going, which isn't guaranteed, but we're making a prediction based on the current data. Okay, that's our goal today, looking at graphs and making the prediction. In your homework, you're going to have to make the graph, some of the graphs, and make the prediction, so be aware of that. All right, let's go to the back side, example 2. All right, use the distance time graph to answer the following questions. All right, so let's check this one out. we've got the skydiver's distance fallen versus the time. So time is our independent variable. So I'm going to put down here independent. And the distance is the dependent variable. So that says DEP. I kind of wrote it sideways. Doesn't really look very good, but it's dependent. All right, so let's look at the question. How far has the skydiver fallen after 10 seconds? All right, so we're going to start drawing those lines. So 10 seconds. Okay, let's go. We'll try to do a better job of going straight up from 10 seconds. Okay, 10 seconds, and then track that over. It's a little high. What would you say that is? 10 seconds is about 1,300 feet. Okay, so A, we would say, at 10 seconds, he has fallen about 1,300 feet. Okay, let's do the next one, B then. B says, how long does it take the skydiver to fall 2,000 feet? Okay, so this time we're looking at 2,000 feet, so we need to come over here and go over to 2,000 and then follow 2,000 down. Okay, so right about here. It's a little scratchy. All right, where would you think that is? About 14 seconds? So yeah. All right, so B is 14 seconds. How long it takes a skydiver to fall about 2,000 feet. All right, let's look at C then. Describe the fall of the skydiver in the first 5 seconds, the next 15 seconds, and the final 10 seconds. Okay, that one's a little bit tougher. Okay, but let's do that one. So the first 5 seconds, so that's from here to here on the graph. All right, they've fallen about 500, about 500 feet in about 5 seconds, if I was to look at that. So we can describe, we could say if it's 5 seconds and 500 feet, we're going to say it's a he. So he fell about 100 feet per second there, right? Because it was 500 feet per 5 seconds that he fell. Okay, then it says the next 15 seconds. All right, so let's break that down. The next 15 seconds would be from 5 to 20 seconds. Okay. What do you think about that? It looks pretty constant. If you look at that, like right here where we notched this, if you didn't notch that, it looks like there's a kind of a curve in the graph. And then it gets constant. It was steady. So we could say he falls at a steady rate for the next 15 seconds. Okay. So our conclusion on the first one, that he fell about 100 feet per second, maybe isn't accurate. Like it looks like that's really inclined. I mean, like, we see that, but that curve, like the rate just changed in between here, right? The rate kind of changes in between here. All right, and then it says in the final 10 seconds. So let's look at that final 10 seconds. So from here, okay, to here, that final 10 seconds. What would you say about that? Okay, the graph is kind of flattening out. So he's falling at a slower rate, we could say. All right, so he is falling at a slower rate the last 10 seconds. Okay, and again, that's because we can kind of see that the graph is flattening out here. It's getting flatter. It's not as steep as it was. All right. So we can answer the questions, make those predictions or approximations in this case, and then draw some conclusions. All right, let's look at the last example, example 3. Okay, so the Wadsworth spent a day hiking in the mountains. Mrs. Wadsworth's GPS-enabled sports watch records her heart rate and position, including altitude. Analyze the following graphs produced from their trip to describe their hiking during each period of time. Okay, so we've got several periods of time here. So here's the thing. Time is our independent variable in both of these. Okay, so time is independent in both. All right, so in the first one, we're talking about time and the heart rate. So I'm just going to put HR, and that's dependent. And the other one, it's the altitude. I don't really have room to get it in there. So altitude is dependent. Okay. But we kind of need to look at these, and then we have these time periods. Okay, so we have time period A is between here. Right, we can see what's happening. We kind of need to look at these together to be able to make our conclusion. So let's say time period A. All right, so what is she doing and what is her heart rate doing? Okay, so if we notice, her altitude is increasing. Well, if she's increasing her altitude, that means she's what? Like she's hiking maybe like up a slope, right? She's climbing up a mountain. So in A, she's climbing up a mountain, and what's happening? What's going on with her heart rate? It starts here, it shoots up real fast, and then there. So what can you say about her heart rate? Okay, you could say her heart rate rose or it elevated. All right, so we can say her heart rate rose as she climbed or hiked, whatever, right? She's hiking, so we're saying as she climbed a slope. I don't want to call it a mountain because we don't know how big it is, but it's a slope. All right, so her heart rate rose, okay, or it was elevated. All right, so let's look at the next one, B. Okay, so that's here, what's happening. So again, let's look at the altitude. So she's just hanging out at the same altitude. So is she climbing another slope or a mountain? No, she's not. She's just walking around at the top of that mountain. We'll call her that hill. So what's her heart rate doing? Okay, well, it dropped. It looks more normal, right? Because this is kind of her normal range. So her heart rate dropped or returned to normal. All right, so I'm going to say HR for heart rate. Her heart rate returned to normal while she walked on the top of the slope or of the hill. Again, I don't know if I want to call it a mountain. Maybe it is. We don't really know. All right, next we're ready for C. All right, so what happened in time C here? Well, that's interesting. Her heart rate, okay, so her heart rate jumped up, so it elevated. But what happened here? What did they do? See, I couldn't trace that. All right, they walked down, not all the way down, but they walked down the mountain. So we're going to say her heart rate elevated. Did it elevate as high as the first one? Okay, no. So we could say elevated slightly, because it's not as much as the first time. Her heart rate elevated slightly as she hiked partway down the mountain. Or just, we could say partway down. Because again, all the way down would have been way down here. So she only went partway down. Awesome job. Okay, let's look at section D. So it's a short little one. Whoops. Okay, so her heart rate, wow, jumped up high, got even higher than the first time. So her heart rate really elevated. And what was she doing? She's walking up, right, another slope. And it looks even steeper, right? She's going up higher. It's even steeper because this slope is steeper than our first slope in A. So in D, her heart rate, we could say elevated greatly, or rose. Her heart rate elevated greatly as she climbed. Remember, it was a steep, so it's a steeper slope. And we could even say than A. Okay, so we could get that in there. Okay, so let's look at the next section, E here. All right, so if we look at E, we look at those together. So her heart rate was like, came down, right? And there it is. Her heart rate dropped. And what's she doing? Her altitude is staying steady. So what's she doing? She's just hanging out, right? At the top of the second mountain. So let's say at the top of the second mountain, her heart rate, again, kind of returned to normal. Return to normal. And you could say dropped or dropped to normal, something like that. And the last one is F. So that's the rest of it. So from F, let's look at what she's doing. Her altitude is decreasing, so she's climbing down this mountain. And what's going on? What did her heart rate do? Okay, so her heart rate elevated as she's climbing down the mountain. Okay, so her heart rate elevated or rose again, we could say. Not nearly as high as it had been. So again, we could say kind of rose slightly. Her heart rate rose slightly as she climbed or hiked, whatever you want to use, down the mountain. Okay, so sometimes we have to use two graphs in conjunction with each other and understand what really each graph means. But when we look at them that way, we realize it makes sense. Like we could learn a lot from looking at these two graphs together. Okay. So your homework tonight does have like 21 through 34 all, because there are some questions like this in there for some of those, like 4 or 5 questions are all on one or two graphs. So you have to, it would help if you looked at all of the questions in there versus just the odd ones. So it is not a misprint. It is supposed to be all. All right, have a great day. And remember to get started on your homework. Keep your conversations to a minimum because the sub is checking that as well. And so we'll talk about that tomorrow. All right, hope you guys do awesome. I know you will.